Hello, everyone. Welcome, everyone, again to another session of the Data Science Summer School 2023 with Calculus for Data Science. We assume that the majority of you here have already attended previous sessions in linear algebra, R, and Python programming, so we can skip the lengthy introduction today. Just a reminder that since this question comes up quite often during the summer school sessions, everyone that registered for the summer school will receive a certificate of attendance, and it will be shared a shared certificate for all the sessions and not for individual sessions. And we will send everyone a link to retrieve your certificate at the end of the summer school next week on Friday. And we will also update the course page on the summer school websites with materials and recordings immediately after every session is over, so that you can watch it back and also practice with the exercises as well. And with that, Sir Prism, the floor is yours. Please take it away for the Calculus for Data Science session today. Thank you.
All right, thank you very much, Joey, for the introduction. And yeah, I would first share my screen. All right, so I hope everyone can see my screen. So today's workshop is going to be about calculus for data science, and it is just another workshop, part of the Hertie School Data Science Summer School 2023. To give a brief introduction about me, my name is Shresim Sadiko. This is my email where I can be contacted regarding any questions that might arise from the workshop today. You also here can see my personal website. This is where you can find all the materials from today's workshop and also the materials of linear algebra for data science, which was yesterday. Some more information about me. I'm a PhD candidate in mathematics at the Technical University of Berlin, and my main area of research is actually robust machine learning. So I'm working on adversarial attacks and questions concerning the adversarial attacks of neural networks. I'm also affiliated with the Zuse Institut Berlin, where I hold a scientific assistant position. And yeah, in general, I'm passionate about artificial intelligence. This is technology that is revolutionizing the world today, and it is being deployed in many real-world applications. So I think not only we should apply it and be aware of what it's capable of doing, but we should also be concerned about what it should not be doing. And on my free time, I usually like to travel and also go to fitness. So yeah, whenever I'm not doing mathematics, I usually like to do this. All right, so why data science? I think we've all seen the tremendous success that deep learning, especially, which is a very special and very highly used branch of data science nowadays. And just to show you some applications where we have seen, the slides are on my website. I can just write down here. All right. Yes, so one of the very interesting applications of data science is in computer vision, for example, and in robotics. We've seen self-driving cars, which nowadays are able to achieve a very high accuracy. But this is still sort of work in progress, and actually big companies such as Tesla and other car companies are investing a lot in improving their self-driving cars. And in general, also we've seen a lot of applications in robotics with data science. Some more applications from computer vision are, for example, in image compression. So for example, if we are given an image and we want to reconstruct it, then using techniques from compressive sensing, we are able to optimize the latent space such that we reconstruct this image in almost real time. Just an application for this, for example, could be when you sort of want to post a video, let's say on your Instagram account, then what your Instagram is doing, it's taking your original video from your iPhone or from your phone in general, and then it's just doing a reconstruction of this video, and then it is posting for you. And of course, this is also one very active area of research, because we want the reconstruction to be as accurate as possible, but also not losing so much time while we post it. So we want to post it really quick, but also in high quality. Or also another application is in noise reduction. So we are given noisy images and we want to remove the noise out of these images. And we've seen applications using variational autoencoders or more traditional image processing techniques such as JPEG compression, etc. Another very important application is in natural language processing. So natural language processing is another branch of deep learning that deals with text data. And one very important application here is, for example, Google Translate. So using this application, now we're able to just sort of scan some text from any language, and then we are able to translate this text in our native language. All right. So yeah, we have all these really impressive applications of deep learning in practice. And then we might ask the question, okay, we want to do data science, but what are the prerequisites for doing data science? When it comes to the mathematical background required for doing data science, then the three areas that are involved with doing data science are linear algebra, calculus, and statistics and probability theory. For those of you that want to know more about linear algebra, then there is already a tutorial by the Hertie School from yesterday on linear algebra. Today we're doing calculus, and tomorrow will be the tutorial on statistics and probability theory. So yeah, these three areas are actually the main areas of mathematics that are involved with doing deep learning, and they can be studied all together or also in isolation. But yeah, today we will focus more in calculus. Just to give a brief outline about what we're going to talk about today, we will first start with looking at variables and functions. So we want to know what is a variable and how we define a function. We will then see the definition of limits. So this is a very important concept whenever we have something's converging to some point but never reaching it. So then we have the concept of limit. We have the concept of the derivative and the integral then, which are opposite of each other. So derivative and integrals are opposite of each other. Then we will see one very important application of the derivative, which is highly used in machine learning, especially applications, for example, in adversarial attacks. What most of the people do is just they apply gradient descent on some certain loss function, and this is like the simplest method you can use. It's also the so-called first order optimization method, when you simply want to minimize loss function over a lot of variables. Then we will look a little bit into matrix calculus, and then we will see the definition of the Hessian. We will see least squares, which is an application in machine learning. We will see how we can look eigenvalues, which we saw yesterday in linear algebra, as an optimization problem. Then we will go more into the deep learning part. And again, in deep learning, we want to optimize these parameters of the neural network. And for that, we actually need optimization. So for that, it is crucial for us to know calculus so that we are able to calculate the gradients with respect to all the parameters such that we can optimize them and find the optimal neural network. We will start by seeing the perception algorithm, which is the first and the simplest concept in deep learning. Then we will see that we can derive perceptron via gradient descent. Then we will see gradients of a neural network. We will see numerical gradient computation. Then we will talk about backpropagation algorithm, which is an algorithm to optimize the parameters of a neural network. We will see the chain rule and the multivariate chain rule. We will see backpropagation through an example. Then we will formalize the backpropagation. We will see some questions that arise in backpropagation, such as vanishing gradients. We will see that the choice of nonlinear activation functions will be crucial for our backpropagation technique. And then we will see that today actually exist automatic techniques, which you can simply use on your computer, which will do backpropagation in a fast way for you. Also, we'll see throughout the lecture a lot of applications, which we will also try to implement in Google Colab in a Jupyter notebook. I will share the link a little bit later when we go to the practical part. All right. So without further ado, let's start with calculus for data science. And the first and the simplest concept is the concept of numbers in calculus. So first, when people started doing mathematics, they had the definition of natural numbers. And these are numbers such as 1, 2, 3, 4, 5, up until 9. And then people realized that they actually need to quantify amounts bigger than 9. So for that, they introduced 0, such that then we are able to define numbers which are greater than 9, such as 10, 1,000, etc. After we had the definition of the so-called natural numbers, we had the definition of the integers. And these are numbers the same as natural numbers, but also including the negative numbers. And the definition of integers is very important, for example, when it comes to finances, where we want to measure profits and losses. So this is a good way to denote such concepts in finance, but there are applications elsewhere as well. Then we have the definition of rational numbers, which is any number that can be expressed as a fraction. So these are numbers such as 2/3, 687 over 100, 2. So as we see, also integers are actually rational numbers. Well, this is easy to see because the number 2, for example, can be expressed as 6/3. So we express this as a fraction of 6 and 3. And rational numbers are called rational, well, because they are ratios. They were quickly deemed necessary because time, resources, and other quantities could not always be measured in discrete units. Milk, for example, does not always come in gallons, so we have sometimes to measure as parts of a gallon. And this is how rational numbers were developed. And one thing that we have to note is that all finite decimals and integers are also rational numbers. So for example, we saw that the number 2 is actually also a rational number. All right, so after the definition of rational numbers, we have the definition of irrational numbers. These are numbers which cannot be expressed as a fraction. So for example, we have the number pi, we have square root of 2, we have the number e. So these numbers are an infinite number of decimal digits. So here, for example, we have an infinite amount of decimals after the dot. And one very interesting exercise is, for example, to prove that the number square root of 2 is irrational. And the proof for this one is actually really simple. I can just give some hints. How we would prove this is by contradiction. We would assume that square root of 2 is actually a rational number. Let's say it's m over n. And one thing that we have to note is that these two m and n don't have any common factor, so they cannot be multiples of each other, for example. And then if we simply square this expression, then we get, so from this we get that m squared is 2n squared. So from here, we see that m actually has to be an even number. So it has to be something like 2k. As soon as we have this, then we can simply substitute it. And if we again do this, then we have which means that n also has to be an even number. So both of them are actually even numbers, but this is actually contradiction because here in the beginning, we assumed that they don't have a term which is common for both of them. But here we see that they actually both have 2. So this contradiction that we got means that square root of 2 is actually an irrational number and it doesn't fall into the category of rational numbers. After we had the definition of irrational numbers, then we have the concept of real numbers, and real numbers are numbers which include both rational and irrational numbers. So this is sort of every possible number. After real numbers, we also have the concept of complex and imaginary numbers. These numbers are usually encountered when we take the square root of a negative number. For example, in data science, this is useful when we do matrix decomposition. So we have to deal with the square root of negative numbers. That's why we need the definition of such numbers. But from my experience in data science, I would say that sticking to real numbers, or like most of the applications are actually dealing with real numbers. So this is the category that we will focus the most. All right, then one important concept is the order of operations. So far we have defined all these categories of numbers, and then we want to know how we actually can do operations with numbers. And as a rule, we have this pipeline on the order of operations. So first we do operations which are on the parentheses, then we do exponents, then we do multiplication, we do then division, addition, and finally we do subtraction. So here, for example, we have on the right, we have a very simple example where we are multiplying 2 by the fraction of the sum of 3 plus 2 squared over 5, and then we are subtracting 4. So how we do this, we first do the operations on the brackets, which is the summation of 3 and 2, which is 5. And then on the second step, we square the 5, which is 25. And then we do the multiplication. So we multiply 2 by the fraction of 25 and 5. This is 50 over 5. Then next we do division, so 50 over 5, this is 10. And finally we do subtraction, so 10 minus 4, which is 6. All right. So this is the order of operations. Then we have the definition of variables and functions. By definition, a variable is a named placeholder for an unspecified or unknown number. And the variables are usually denoted by Greek letters such as alpha, beta, theta, etc. And a variable can represent any real number with which we can do math operations with. Functions, on the other hand, are useful because they model a predictable relationship between variables, such as, for example, how many fires, y can we expect at a temperature x? And they define relationships between 2 or more variables. So for example, if we take input variables, we plug them into an expression, this will result in an output variable. So here, for example, we have this very simple example. We have y, which is 2x plus 1. So x is sometimes also called the independent variable. Well, because x is not depending on any other variable. And y, on the other hand, is called the dependent variable. Well, y is a dependent variable because it needs a value for x. So it is dependent on x in order to have a value for itself. And here on this table, we have depicted the values of y for 4 values of x. For 0, 1, 2, and 3. So for x0, we just multiply it by 2 and we sum it with 1. So we have a value of 1 for the y, and so on and so forth for the other 3 numbers. Another way to represent this equation is on using this notation. As I said, y is depending on the variable x, so we might as well express this as f of x. All right. The next concept that we have is the concept of continuous functions. So when we make steps of x infinitely small, then this function that we had from before to x plus 1 is actually a continuous function. So again, we have 2x plus 1. And so far we tried x. We can actually have multiple values for x. We can have infinitely many values for x. So all these values here, this is so-called the x-axis. For every values of x on the x-axis, we have a corresponding value on the y-axis. So not only we can try for these 4 values, but x can be anything from minus 10,000 to 10,000. And if we want to plot then this function, so for x0, the value of y is 1. So we are here in 1. For 1, we are at 3. So let's say here is 1, we would be here at 3. So this would be the corresponding value. And if for 2, this would be at 5, and so on and so forth. We have many values on the all right. So yeah, we have two exercises, f of x, x squared plus 1, and then what we can actually do, we can also plot functions not only of one variable, but functions of multiple variables. So in this case, we have two independent variables, x and y, and we want to plot the function f of x and y, which is 2x plus 3 epsilon. We will see this later in the coding part, how we can plot it. One thing to note in here in the continuous functions is that when a function is continuous but curvy rather than linear and straight, we call it curvilinear function. So we could have something like this would be the x-axis, this would be the y-axis, and we could have a function which is something like this, parabola. This is so-called a curvilinear function. All right, so after we have defined continuous functions, we have the definition of a logarithm. So the logarithm is a math function that finds a power for a specific number and base. There's one question: what if we change the order of dependent variables? For example, 2x plus 1. Yes, we can arrive. All right, so yes, here we have 2x plus 1, so we have modeled variable y in terms of the variable x, but we can then, this is the so-called explicit formula. From this, we can also express x in terms of y. So we can express the independent variable in terms of the dependent variable. And which one is the dependent one and which one is the independent one? This has to be clear from the application that we have in hand. So here we would have y minus 1 equal to 2x. So we could simply express x as the fraction of epsilon minus 1 over 2. So yeah, this has to be clear from the application that we have in hand. Yes, so we were left at the definition of a logarithm, which, as I said, is a math function that finds the power for a specific number and specific base. Why do we need the definition of logarithm? Well, the definition of logarithm is very crucial in measuring earthquakes, for instance, or managing the volume on the stereo that we use. And when it comes to machine learning, the definition of logarithm is crucial for defining the logistic regression. So one example here, we have 2 to the power of x equal 8. And how we could express this in terms of logarithm? Well, as we said, logarithm is the function which finds the power for a specific number and base. So here the power would be x. So we could express this as the logarithm of 8 with base 2. So we want to know to which power do we want to raise 2. So this is the x, such that we get 8. And by simply doing some powers of 2, for example, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8. Then we can see that the power that we actually need is 3. So the x in this case is 3. In general, we can write this as x is the logarithm of b with base a. So when we raise a to the power of x, this gives us the b. And when it comes to applications, the default base in earthquake measurements is 10, whereas the default base in data science and Python is the so-called number e, which is also called Euler's number. We will see the definition of it in a bit. Some properties of the logarithm is that the logarithm of the multiplication is equal to the sum of the logarithm of a and the logarithm of b. The logarithm of fraction of a over b equals the difference between the logarithm of a and logarithm of b. The logarithm of a to the power n equals n times the logarithm of a. By definition, the logarithm of 1 is equal to 0. This is actually easy to see. So if we denote the logarithm of 1 by x, then this should have the base 10. So we want to find the x such that when 10 is raised to the power of x, it gives 1. So what is the power that we can raise the 10 such that we get 1? Well, we all know that for x1 or x2 or x3, we would have 10 to the power of 1, which is 10, 10 to the power of 2, which is 100, 10 to the power of 3, which is 1,000. So what we could do is we, by definition, raise it to the power of 0. So 10 to the power of 0 is 1. This means that x is 0. Also, another property is that the logarithm of x to the power minus 1 is minus the logarithm of x. This is also easy to see. Well, logarithm of x to the power minus 1 is equal to the logarithm of the fraction of 1 in x. This, by the second property, is equal to the logarithm of 1 minus the logarithm of x. By definition, the logarithm of 1 is 0, so we have 0 minus logarithm of x, so this is simply minus the logarithm of x. All right, so as I said, now we will define Euler's number, denoted by this small e. So by definition, e is the resulting value of raising this expression 1 plus the fraction of 1 and n to the power n as n gets bigger and bigger. So if we try to find the value of Euler's number for some values, we will see that, for example, 1 plus 1 for this is for n 100, this is for n 1000, this is for n 10,000, and this is for 1, 2, 3, 4, 5, 6, 7. So yeah, for n100, we have 1 plus 1 over 100 raised to the power 100. So we have this number over here. And then we have this number, and then we have this number, and finally we have this number. So what we see is that all these numbers have this common 2.7. And here also 1 in the last 3 numbers. But the other digits actually differ a bit from each other. But what we can see is that as n is getting larger and larger, then this number of Euler, epsilon, E, is converging to this one. And why do we need the definition of Euler's number? Well, this number is used not just in studying populations and their growth, but it also plays a crucial role in many areas of machine learning as well. So the definition of such a number is very crucial for data science. All right, so far in the Euler's number, we saw that if we have sort of an expression of this form, if we keep increasing the number n, this sort of expression is converging, as we say, towards some number. But at the end of the day, since we earlier defined functions, what this expression is, it's actually just a function of the variable n. So we can denote this in this way: f of n equals 1 plus 1 over n raised to the power of n. So what we could do, can we plot this function? And for a continuous n being a continuous variable, so taking infinitely many values, then f of n is also continuous. Having defined this concept of something converging towards something, we can actually give the definition of the limit. So from the previous slide, the number e means that while we increase the input variable, then the output keeps approaching a value, but it never reaches it. So as x increases forever, then f of x gets closer to 0, but it never reaches it in this case, for example, when f of x equals 1 over x. And actually, in this example, we have depicted how this function looks graphically. And as we can see, so here, this would be the x-axis, and this would be the y-axis. So when x is tending to infinity, then the value of this function is actually converging towards 0. And how we could write the number e in terms of the limit? Well, as I said, in this case, f of n is 1 plus 1 over n to the power of n. So then we say that the limit of 1 plus 1 over n raised to the power n, when n tends to infinity, gives the number e, which by definition is just this number, 2.71828. So this would be the part that we need to memorize. All right, so now we have also given the concept of the limit. And after we have given the concept of the limit, we are ready to talk about derivatives. Let me first check the chat so we don't skip any question. All right, so there's a question, shouldn't the value be at 1? I guess the question is that if we were to have an x here, then its y value would be something like 1. Well, yes, this is true, but our idea here is that we want to know what is the value of this function when x tends to infinity. So we don't want just for x equal 1, 2, 3, like for certain values, but we want the value when x tends to infinity. So that's why we get that the value of this function when x tends to infinity, it is 0. All right. And next we have the concept of the derivative. By definition, the derivative gives the slope of a function. So we want to measure the rate of change at any point in a function. And this is simply done using the derivative. And one very important application of derivatives in machine learning algorithms is that they are used, for example, using gradient descent. So by definition, if we were to minimize a function f of x, let's say, then how gradient descent would find its iterates would be minus some lambda, the gradient of x. So yeah, we need the definition of the gradient to do, for example, gradient descent. All right, and when slope is 0, so when the derivative, and we have one thing that we have to know is that the derivatives are simply denoted by this expression when we take the first derivative, or this is the second derivative, or when we are dealing with partial derivatives, then we denote this and this. But we will see this more clearly in the next slides. All right, so when the slope is 0, when the derivative is 0, then we are at the minimum or maximum of an output variable. So here on this example, we have depicted the function x squared, which is just a parabola starting from 0 and spreading up. And we sort of want to know how we could find the slope of the tangent of this curve at any point. So for example, here we have the slope at for x equal 2, we want to know the slope of the function f of x equal, x squared. So in other words, the derivative measures the steepness at any point in curve, and it is visualized with a tangent line. So for example, we could take x2 here and just a point very close to it, 2.1. And then if we were to calculate the values for these 2 points, then we would have f of 2 equals 2 squared, it would be 4. And f of 2.1, it would be 2.1 to the power of 2. This would be 4.41. And if we want to calculate the slope m between these 2 points. And then by formula, for the slope is y2 minus y1 over x2 minus x1. And we simply plug the values that we found before. So y2 is simply f of x2 and y1 is f of x1. So we plug the values that we found before, 4.41 minus 4.0. And for x2 we have 2.1, for x1 we have 2.0. So we get just a value of 4.1. What we could do is that we could further take a point which lies between these 2 points. So point in between these 2 points would be, for example, 2.0001, or yeah, we could have even more zeros over here. And then the value of x for this would be simply raising this value to the power of 2, and we would get something like this. So this value again is very close to the actual slope of 4. Because as we will later see, by definition, the derivative of this function x squared is actually 2x. So for x equal 2, the actual slope is 2 times 2 equals 4. So as we see, for 2 points which are not so close to each other, this value is higher. And when the 2 points are getting closer to each other, then this value is actually getting closer to the actual value of 4. By definition, exponential functions such as x squared, for example, its derivative will make the exponent a multiplier and will decrement the exponent by 1. So the derivative of f of x, in this case, of x squared, we make the exponent a multiplier. So we take the 2 in front, and we decrement the exponent 2 by 1. So this is simply 2 of x. So yeah, we either use this expression 2d over d of x of f of x, or we could also use the expression just like this. So we take the 2 in front. So this just gives 2x. And as I said, when we want to calculate this slope of the function x squared at point 2, we simply plug the 2 instead of x, and then we have 2 times 2 equal 4. As we will later see in the practical part, we mostly use the library SciPy to calculate the derivatives. And the formal definition for the derivative is given by this formula. So we want to find where this slope m is converging when these 2 points are getting closer and closer to each other. So before, in the application that we had before, so we had 2, and then we want to make this difference between x2. So 2 was x1 and this was x2. So we want to know when this difference between x2 and x1 goes to 0, we want to know where the expression is converging to what value. So yeah, we can express x2, which before was 2.1 or 2.00001 or something like this. We can express x2 either as x2, or it is simply x1 plus x. Or if we don't have this notation with x2 and x1 anymore, we just denote it as x plus s. And yeah, here, for example, we find that the limit when, I think I made a mistake here, s tend to 0 of 2 plus s squared minus 2 squared over 2 plus s minus 2 equals 4. Again, I mean, I don't want to go so much into details. What is s? One question. Well, s, as I said, is this change that we have on the x-axis from the point x1 to the point x2, because we want to find the slope of this tangent line. And in order to find it, we need to have 2 points for it, right? Because every line on two-dimensional space is defined by 2 points. And in order to find these 2 points, then we usually take 1 point here and the other point very close by to it. And then we just find the limit when this difference between these 2 points goes to 0. Again, I was saying that there actually exist a lot of techniques how to find the limit of expressions and a lot of rules. Yeah, I mean, usually for data science, if you are not really so much concerned with doing limits, but you just want to finish your application, that I would suggest that you use the already implemented libraries such as SciPy, which does calculate the limits automatically for you. All right, we will actually see some examples in a bit. All right, so after we have given the definition of the derivatives, we can define partial derivatives. So far we had functions of one variable x. So let's say we had 2x plus 1, we had x squared, etc. But we could, as we saw, have functions of two variables. For example, 2x squared plus 3 epsilon minus x plus 2 epsilon, etc. So as soon as we have functions of two variables, we want to find the slopes with respect to multiple variables in several directions. So how we do that is that for each given variable, we simply assume that the other variables are constant. So for example, if we have f of x epsilon equals 2x squared plus 3 epsilon, then we could simply, if we want to find the derivative of f with respect to x, then we could simply consider the variable y as a constant. So we would simply need the derivative of 2x squared. As we saw from before, the derivative takes the exponent to the front. So it's 2 times 2 times x and decrements the power by 1. So this is 4x. if we were to find the derivative of f of xy with respect to epsilon, then we keep the variable x constant. So then we would have d over dy, 3 epsilon. The power here is 1, so if we take it in front, it's simply 3. We decrement the power by 1. So this gives us simply 3. So the two partial derivatives are 4x and 3. We have yet another example. So we have this function. Again, how we would find the derivatives of this function, we simply write it down. We remove, or we consider it to be constant, and by definition, the derivative of equals 0. So we would have here, considering this as a constant, we would have the derivative of this expression. Again, we take the power in front, so this is 6, we decrement the power by 1, so 6x squared. And similarly, we have y. We take the power in front, 3 times 3 equals 9, we decrement the power by 1. So this is how we get the two partial derivatives. All right, and then for two values of x and y, so let's say 1 and 2, and then the slope with respect to x is we simply substitute x here, and we substitute y here. So x is 1, 6 times 1 is 6, and y is 2, 9, 2 to the power of 2, this is 36. So yeah, we have the step size s, which is forever approaching to 0, but it's never reaching it. So otherwise we would have no line. As I said, the line needs 2 points in order for it to be defined. So in the example that we had before, we converge. So like on this example that we had before, for 2, we converge at the value of 4 for epsilon. All right. After we have defined the partial derivatives, we can look up into the so-called chain rule. So what happens in the chain rule is that we can have variables which are dependent on other dependent variables. So for example, in this slide, we have y, which is equal to x squared plus 1. So x is the independent variable, y is the dependent variable. But then we have z equals to y cubed minus 2. So y is, in this case, the independent variable, and z is the dependent variable. But actually, y is dependent on its own on x. So what we could do in this case, we could simply plug this value of epsilon into the equation for z. So we would have z equals to x squared plus 1 to the power of 3 minus 2. And then we want to find the derivative of z with respect to x. So how we would do that? We simply plug down the value of z. And then there are two ways to do this. Now, first, we could either open this up and then just consider this as a function of x, or the other way that we can find is that the derivative of this expression here, we simply apply the rules that we saw from before. So it is 3 x squared plus 1, 2 times the derivative of the expression that we have inside, because we didn't take the expression, the derivative of this expression. And minus 2, we can remove it because it's just a constant. So this is 3 x squared plus 1 squared. Again, the derivative now of this other expression, we have the derivative of x squared plus 1. So we take the power in front, we decrement the power by 1. So we can take everything in front, and this would be 3 times 2, 6, x squared plus 1 squared. All right. So yeah, we have the same result here, actually. But what we could do in a second approach, so this so far was the first approach. As a second approach, we could take the derivatives of y and z separately, and then we could simply multiply them. So the derivative of y with respect to x of x squared plus 1, this is simply the power goes in front, and we decrement it by 1 to x. And the derivative of z with respect to epsilon, 2 is a constant. We take I did a mistake here again. All right, so then we simply multiply this two. So the dz over dx is simply dy over dx. No. It's dz over dy times dy over dx. And if we plug the value for this one is 2x, and the value for this one is 3y squared. So multiplying them together, we get 6xy squared. And by simply substituting y from above, which is x squared plus 1, we would get 6x, x squared plus 1 to the power of 2, which is the same that we had from before. So by definition, the chain rule is what we just wrote here. So the derivative of the dependent variable z with respect to independent variable x is equal to the derivative of the dependent variable z with respect to the intermediate variable y times the derivative of the intermediate variable y with respect to the independent variable x. So I'm just reading the comments whether I've skipped some question. All right, so I think all the questions have actually been answered. Y is 6x squared equals to 6x. Well, if you mean the expression here, well, we just substituted the value for y that we have here on top. So we simply plug in the value for y, and that's why we get 6x squared plus 1. All right, so now that we have defined and derivatives, we can give the definition of the integrals. So by definition, derivatives and integrals are two opposite operations. So the opposite of derivative is the integral. And by definition, the integral finds the area under the curve for a given range. So in this case, we are given this function as depicted here. And let's say we want to find the area which lies from range 2 to 3 and lies under the curve which is simply 2 times x. So we want to measure the area under the line between 2 and 3. But as we know from basic geometry rules, area for a range under straight line is actually really easy. So from basic geometry, we already know how to find areas of such objects or such objects or so in this case we would just have A times B. In this case we would have well, if we would denote A, B and this H, we would have H. So the areas of such geometric shapes are easy to calculate. So whenever we have a function which is of this form, so for example, we could have a triangular here, or this would be the trapezoid that we saw, or we could have a function which is like this. So this would be, for example, simply y equals 2, and we would like to find the range between 2 and 3. So all these areas is actually really easy to find the surface or the area. And for example, in this case, we simply have that the area of the trapezoid is 4 plus 6 over 2 times 1, and this is simply 5. So then in this case, the definition of the integral is actually really straightforward, so we don't have to do much. But the difficulty arises when the function in hand is more difficult. For example, we could have something like this. So f of x, for example, could be x squared plus 1. So as we saw from before, the x squared passes through 0, 0. But when we have +1, then this is just shifted. So it starts here from 1 and not anymore from 0. So this is just shifted. And what we want to find, again, is that we want to find the area between 2 and 3, which lies under this curve x squared plus 1. Well, now the problem is that actually from basic geometry, we don't know how to calculate the area of such a surface. So if we had a clear formula in the previous slide for these simple geometric shapes, now we don't have any more easy formula to do such a calculation. So curviness does not give a clean geometric formula to find the area. What we could do in this case, so let's say we have this area now. What we could do is that we could try to pack 5 rectangles of equal length under the curve, where the height of each one extends from the x-axis to where the midpoint touches the curve. So we could split this into 5 equal rectangles, and the midpoint so we have something like this. All right, so as you see, for example, here we are losing a little bit of space, but here we are gaining a little bit of space. And so on for the other rectangles. But what we see here is that actually we have some way to approximate this area under the curve. And what would happen if we were to have more rectangles? Then the more rectangles we would have, the better this approximation would be. So if we would do more such rectangles, then we could even better approximate the area under this curve. So sort of we see that the margin to which we do a mistake gets smaller and smaller and smaller. So this is yet another concept of increasing, decreasing something towards infinity to approach an actual value. And yeah, so this is actually this is the definition of the integral. So if we then would do this towards an infinity, so like if we would keep increasing this number of rectangles more and more, then this would sort of approximate us the area under the curve that we have. And the integral approximation in Python is actually really straightforward. So how we would do, for example, to calculate this area, we want to calculate this area over here. And then we first start to define this delta x, which is b minus a over n. So note that this is a would be here, b would be here, and n is just the number of the rectangles that we want to have. And then what we want to find is we want to find the value of this rectangle in the middle. So we want to find where this rectangular is touching actually the function x squared plus 1. So as soon as we have the value here, at this point over here, then we have the height of this rectangular, and then we also have the width of the rectangle. And as soon as we have these two values, we can simply calculate the surface, which is a times the height. But actually, these a's are the same for all these rectangles. So we, depending on how coarse we want to go, by increasing this n, at these values, delta x are the same. So it's delta x times h. And they all have different heights. So this would be height 1, let's say. This other one would have a height 2. The third one would have a height 3, height 4, height 5, and so on and so forth. But they all have the same width. So the area of the first one would be delta x times h1 plus delta times h2 plus delta x times h3 plus. So we can just take delta x in front, and we have h1 plus hn. So we have here now in the code, this is the part that we are calculating this midpoint. So these midpoints are h1 to hn. And then what this total sum is doing, this total sum is just calculating these sums over here. And what we finally return, we just multiply this total sum that we found by this delta. So we multiply the total sum by the delta. And then we can simply apply this for our example. We had the function f of x squared plus 1, which we want to integrate in the range from 2 to 3. And we want to have 5 rectangles. But actually, as soon as you have implemented this code, you can increase the number n to as many as you want, as many rectangles as you want. Okay, so someone is asking to repeat the for loop. So yeah, in the for loop, we are just calculating this midpoint, and these midpoints are just these values over here. So if we have, let's explain it here. So this is our function, and for example, here, this would be one rectangle, so we want this point. And why are we doing this? Total sum times the delta x is just the explanation here. All right. So yeah, here we tried out for 5 rectangles, but we could actually have more rectangles, as I said. So for example, for 1,000 of rectangles, we could have 100,000, etc., etc. So again, we get different precisions here and here. but they all have, up to some point, the same value. So more or less, this is converging to this value. And if it were to be a rational number, that this would likely be 22 over 3. As I said, again, in data science, unless you really want to understand and solve it by hand your integral, in most of the cases, you simply put this into SciPy and you can solve the integral. All right, so then, as I mentioned a bit earlier, we have the concept of the gradient descent. This is a concept used a lot when we want to minimize any objective function. So here we are willing to minimize the function f of x over a certain region, calligraphic x, the so-called domain of x, which is a convex set. So for those of you who don't know what a convex set is, this is, for example, a convex set. A convex set is such a set such that for any 2 points inside the set, the points connecting the 2 points all lie within the set. So an example, a non-convex set would be, for example, this one, this area, X. This is non-convex, well, because if we take a point here and if we take a point here, then when we try to connect them, we would have points which do not lie on X. So yeah, gradient descent is usually used to optimize functions over a convex set X. And the update rule for it is what I also wrote a bit earlier. So in an iterative way, x at the step t plus 1 equals x to the step t minus some so-called learning rate, eta, the gradient of x at point x2. And usually for t0, so on the initial step, we sort of would start at some x0. For example, here on this example, we are starting from, I guess this would be -5. And then we are, by blue, we are denoting the function, which I think is x squared. And then we are doing one step of gradient descent. So x1 is just -5 minus some learning rate times the gradient of f at -5. So this is 2x0 minus 10. So x1, well, in this case, is at -2. I don't really know in this specific application what the eta was, but we can find this easily. So -5 plus. So yeah, we simply equal this expression for -5 plus 10 eta equals -2. We find that eta is 3/10. So then this is the value for the x1. And we repeat this procedure once again. So x2 is x1 minus eta, the gradient of x at x1, and so on and so forth. So then we have this value, then this value, until it converges at 0. So this is the way that we optimize our function. All right, so we actually have an example on gradient descent, which we will try to solve by hand. All right. So you also have the solution on the slides, but I would like to go with you. And solve it by hand. So we have a function of two variables, which is 0.5 x1 squared plus x2 squared plus 2x1 plus x2. That's the cosine of sine square root of p. In point A, we need to compute the minimum x1 squared, x2 squared of f. As we saw before, the slope, which was the definition of the gradient, gives us actually the minimum of a function. So what we need to do in order to find the minimum, we simply calculate the gradient of this function of two variables, which is simply x1 plus 2, and this is 2x1 plus 1. And we set this to 0. So then we just solve this equation, and we get that x1 star is minus 2, and this is 2. X2 star is minus 1 over half. So yeah, we can write this in a vector way. Actually, we could also graphically represent this function. I will just give it for you, but you could try it out. The function looks something. So the minimum is at minus 2x1 and minus 1/2 x2. And actually the function is just some ellipsoid. So this is fx1, x2. All right, so this over here is the actual solution. All right, but now what we want to do, we want to find what happens, or we want to see the gradient descent sort of in action. So we want to, as we are required from the slides, we want to do gradient descent on fx1, x2, starting from point x1 0, x2 0, 0, 0. And we have a learning rate of eta 1. So we are starting from here. All right. So we start with the gradient descent. The first update, we have x1, 1, x2, 1. By the definition of the gradient descent, we have x1, 0, x2, 0, minus the learning rate, times the gradient at the point. But the gradient, as we saw here, this is the gradient, so we simply plug it down. And we have x1, 0, plus 2, 2, x2, 0, plus 1. So now we have everything we can plug in. We have x1, 0, x2, 0. We have the learning rate data. So we have 0, 0, minus 1 times plugging 0, 0. Here we would get 2. Here we will get 1. So we have a minus 2 and minus 1. So by gradient descent, we would go from here, we would go here. So this would be our new x1, 1, x2, 1. At minus 2, 1. The second update would be x2, x1, sorry, x1, 2, x2, 2. I'm sorry if I'm confusing you a little bit with the notation, but these are both vectors. Either one denoting this, x1, x2, but this is also the same vector. So this is just the same vector. So we go back to the second update. And the way that we do it, this would be just x1, 1, x2, 1, minus the learning rate, the gradient at the first iterate. We plug the value for x1, 1 and x2, 1. This is just this value, minus 1, minus 2 plus 2, 2 times minus 1 plus 1. And this simply gives us minus 2, 0. So yeah, this is then from this point here, we are going to this point here. So this is x1, 2, x2, 2. All right. And in C, we are asked to whether the gradient will converge to the of this procedure. So using gradient descent, do we converge to the actual minimum, x1 star, x2 star? So what we do, we check one more update. So the third update, we would have x1, 3, x2, 3. This would be x1, 2, 2, 2, minus the learning rate, x1, 2. So we have the gradient, 2, x1, 2, plus 1. This is minus 2, 0, minus the learning rate, minus 2 plus 2, 0 plus 1. This is minus 2, 0, minus 1, 0, 1. I'm sorry. Zero minus 1 equals 2, 0 plus 1. All right, and this is simply minus 2 and 1. Minus 1. Sorry. So then from here, we go back to here. So this is actually also x31, x13, x23. So this is simply x11, x21. So this value, the third update, goes back to the first update. So this means that we are stuck between x1 and x2 forever. How do we solve this problem? We solve this by decreasing the learning rate. And I would like you to take this as a homework. For example, for learning rate 5/6. For this different learning rate, you don't get anymore this weird behavior that you start from here, then you go here, then you go here, and then you go back here, and then you go back here. So you are not stuck in between these 2 points, but having this different learning rate, you will actually go more towards the optimum, which is here. All right, so this is all for the exercise on gradient descent. And I think we can go back to the slides. All right, so somebody's asking, can you define what learning rate is? Well, yeah, the learning rate, it's sort of this speed with which you sort of converge towards the optimum. So the optimum here would be here. And the learning rate just dictates you how fast you can reach this optimum or how slow you can reach this optimum. And of course, choosing the learning rate is not a trivial thing to do because, well, if you choose a very small learning rate, then you are always just moving with small steps here until you reach the optimum. If you choose a very big one, then you could end up like here. So this would be big. This would be small. So yeah, choosing the correct learning rate, it's sort of what is crucial for the gradient descent algorithm to work properly. But there exists a ton of techniques which already do this for you. I think you can use the adaptive step size, for example, in many applications. All right. I think before we would go to the metric calculus, I would like to do the coding part, and then we could continue with the rest of the slides. All right. The inverted delta sign just means the gradient. What is the intuition logic behind subtracting product of the learning grade times the gradient to reach an optimum? We will see this in the second part, where we will derive the gradient descent via using the partial derivatives procedure. So this will come in the second part. Right. Did I send a link? All right, so let's start with the coding part. First, for those of you who are new to Python, again, as yesterday, there are a lot of tutorials online. You can just pick whichever you like the best. If you never worked with NumPy or Jupyter before, then you can check these guides, which I attached to this notebook. The first task that we want to do is the order of operations, which was one of the very first slides. So we want to implement this expression 2 times the fraction of 3 plus 2 squared over 5 minus 4. And we want to save this into a value, my value. So to implement this, we actually don't need to import any library, but simply do 3 plus 2 squared over 5 minus 4. And then we want to print this value. I think on the lecture it was 6. It's taking a while. Okay, so yeah, it gives us a value of 6. And then we have functions in Python. So we want to implement a function to x plus 1, and we want to print the results for 4 values of x. So first, to implement f of the x, we define the function f of x, and we simply return 2 times x plus 1, and we give it 4 values, let's say 0, 1, 2, and 3, and we just print the epsilon. So we get the corresponding values for the f function. The next task is to plot this linear function. And here, for this, we import the library SciPy, which we said from the lecture that we use a lot for plotting, for finding integrals, derivatives, etc. First, we declare the variable x to SciPy, and then we implement the function f. And then we plot this function. So yeah, this is the function that we had from the lecture. Not only can we plot linear functions, but we can also plot curvilinear functions, which don't have a linear behavior anymore. Again, we use SciPy. We define the function x squared plus 1, for instance, that we have in the lecture, and then we plot it. So we have something like this. And then for the parabola x squared, we want to calculate the partial derivatives and we want to compute the slope. So first we import NumPy. We want to do this exercise with NumPy. And we also import another very powerful plotting library, matplotlib. First, we define the parabola. We simply return x squared. And then we define the derivative of the parabola, which, as we saw from the lecture, this is simply 2 times x. So we take the power in front, we decrement the power by 1. We define x in some range for the parabola from -5 to 5, and we use 100 points. And we choose 2 points. We choose a point to plot the tangent line. Next thing that we want to implement is to implement the tangent line. So we define this line, which takes as arguments x, x1, and y1. And then we return slope of x1 times x minus x1 plus y1. And then we plot this figure, which we again had from the lecture. So we have depicted the function x squared plus 1 and the tangent line at the point 2. At the point 2, right? Yes. So x1 we chose to be 2. All right. And then, as I said, not only we can plot 2D functions, but we can use actually SciPy to plot 3D functions as well. For example, here we have the function 2 times x plus 3 times epsilon, and if we simply plot it, and then, as you see, we have a sort of surface in the 3-dimensional space. The next task is the derivative. So we want to implement the derivative calculator, and we want to calculate the slope at 2 for the function x squared. So what we do here, we want to implement the slope. As we saw from the lecture, the equation for the slope is just f of x plus s, so like this size which we had, which was the difference between x2 and x1, minus f of x over x plus x minus x. So we just have f of x plus the step size minus f of x over x plus step size minus x. And then we return the slope. We define our function x squared, and we're going to calculate the slope here at the point 2 for our function. And then we want to print the slope. So as we see here, the slope is this one. What we can next do is that we can calculate the derivatives in SciPy. So the slope actually from the lecture gave us the definition of the derivative, but we don't need to always implement the slope in this way. We can simply use SciPy to calculate the derivatives. So we just use Python to declare our function x squared, and then we use this command to calculate the derivative of f. So yeah, it prints for us the derivative, which is 2x. And then we want to also find the slope at the point 2, so we just plug in the value 2. So we get 2 times x, which is 2 times 2 equals 4. In the next task, we want to calculate the partial derivatives with SciPy. So we first declare to SciPy the variables that we are operating with, x and y. And then we just use the Python syntax to declare a function. So 2x cubed plus 3 to the power of 3. And then to calculate the partial derivatives for x and y, we simply use the diff command of SciPy to calculate the partial derivative of f with respect to x, and we use the diff command of the SciPy library to calculate the partial derivative of f with respect to y. And we also want to plot this function. So first of all, we get that the partial derivatives are 6x squared and 9y squared. And this is the area of the function. So we don't have a surface anymore, but it's like a curvilinear function in 3D. And next, we want to implement the chain rule. So as we saw from the lecture, this function z was expressed in terms of 2 dependent variables, x and y. Well, y on its own was a dependent variable on the variable x. So the relation between y and x was that y was equal to x squared plus 1. So here we have just plugged in the value for y, and then we have this value for z. Again, we use the diff command of the SciPy library to compute the partial derivative of z with respect to x, and we simply print this value. And again, as we saw from the lecture, this is just 6x times x squared plus 1 to the raised to the power of 2. And next, we want to do the chain rule. So far, we just use a SciPy. We didn't really implement it on our own. So we want to use the chain rule to do that. And for that, we actually don't just use the command diff to compute the partial derivative of z with respect to x, but we first compute the partial derivative of y with respect to x. So we implement this intermediate variable underscore y, which is x squared plus 1. And then we also compute the derivative for the second function. So we again define z as a dependent function on the variable y, which is again on its own dependent on x. And we use the diff command to calculate the partial derivative of z with respect to y. So then, as we saw from the lecture, the chain rule is just given by this expression. So the chain rule was the partial derivative of z with respect to x is the partial derivative of y with respect to x times the partial derivative of z with respect to epsilon. And we simply substitute for epsilon the value of underscore epsilon. And as a numerical check, we just want to show that these two values are the same. So either using the chain rule or not using the chain rule, we get the same value. And as we see, we get the same value. So either if you use the diff command right away of calculating the partial derivative of z with respect to both variables, or if you multiply these two partial derivatives, you should get the same value. And then the next task would be to do numerical integration. All right, so here what we want to do is we simply want to plot the function x squared plus 1 and the area under the curve between 2 and 3. So for that, again, we import a matplotlib library. We set x to be between 0 and 5, and we take 1,000 of the values. So the function that we want to plot, let's say, we use the plt.plot command, and the function that we have is x squared plus 1. And yes, so we want to calculate only the area between 2 and 3. And this is how we plot this area. So then next, we simply want to implement the approximate integral function that we had from the lecture. Well, what we first do, again, as we saw in the lecture, we compute these widths of the rectangles that we had from the lecture. And this is just b minus a over n. And we set the total sum to be 0. And then for each of these rectangles, we want to find the point where the rectangle touches the function at the midpoint of its width. So for I in the range from 1 to n plus 1, the midpoint is 0.5 times 2 times a plus delta times x times 2 times I minus 1. So the total sum and as I said, since all these rectangles have the same width but have different heights, we can sort of just multiply the width by the summation of all the heights. So here we sum the heights of all the rectangles. So we just return the multiplication of the total sum times the delta underscore x. And yes, so this gives us an area of around 7.33. But we can actually use the already implemented function approximate underscore. No, this is the function that we defined ourselves. Yes, so the approximate underscore integral. But we did here for 5 rectangles, so we can do it for 1,000 of rectangles. And this prints a similar area to what we had before, but not quite the same. So we have this 7.33, which is the same. And we can sort of keep increasing this. So as we see, this integral more or less converges towards this point. But as we said, we can use SciPy to already give us this integral for us. And if we simply use the function integrate, we give the function f which we want to integrate over which variable we want to integrate, and we give a range from 2 to 3 that we want to find the integral. So it gives an area of 22 over 3. We can do numerical integration also with SciPy, which is another SciPy, which is another library. So for example, we have this function which we can first implement. Lambda x. Let's implement this as a lambda function, which takes 3 variables x, mu, and sigma. We then use the exponentiate function minus 5 times x minus mu raised to the power of 2 over sigma squared. We plug some values for mu and sigma, and then we plot this function. So this function looks something like this. And what we want to do is that we want to integrate this function between -10 and 12, and we want to print the integral and an estimate of the absolute error. So for this, we use again the integral command from the SciPy library that we saw before. It not only gives us the integral, but also the error. So we just set integral f a b args. And then we print the integral and an estimate of the absolute error of the result. So the integral is this one, and the estimate of the absolute error in the result is this one. All right, so and then we saw so far derivatives, but we can also calculate them using automatic differentiation with JAX, which is another library in Python used a lot in optimization. So we want to take the univariate function derivatives. We have first this function 3x squared plus 2, and we know that the first derivative is well, we take the power to the front and we decrement the power by 1, so it's 6x. The second derivative is simply x. And what we want to do here, we simply implement this function here. And we want to compute the gradient at a point 10. To implement the first derivative, what we need to print is just the gradient of y with respect to x0. So this is evaluated at point x. And then for the second derivative, we just print the gradient of y with respect to x0. So yeah, we get a value of 60 for the first derivatives, which was 6x. So we just plug 10 for the x, and we get 6 for the second derivative. Not only we can do functions of univariate functions, so functions of one variable, but we can also do functions of multiple variables. For example, we have 3x1 cubed plus 2 to the power x2. And the partial derivatives, I would like you to do this as a homework. So it's, yeah, you take the power in front and then you decrement it by 1. Here again, we are required to implement the function of y. Let's implement it again as a lambda function, which takes two input variables x1 and x2. This is just 3 times, we use numpy to raise to the power of 3 plus numpy dot power 2x2. And here, as we see, the gradient of using the grad command from this package actually equals the same as 9x1 squared, which if we substitute the value 2, 9 times 2 squared is 9 times 4 equals 36. And in the same way for x2 equal 3, we would get that it is the same. And one final exercise that I would like to do in this part would be about gradient descent that we saw in the lecture. So we want to, if you want to know more about how we implement gradient descent, we are going to use this library JX. So if you want to read more, you can just click on this link and it will show you all the relevant information. So we have this function now, kx squared plus some constant and k set to 3. So we first import the JX library. We use, again, lambda functions to simply implement our function that we have. And then these are the steps of the gradient descent that we saw from the lecture. So we want to minimize the function f, starting from a point x0, given a step size. So this step size is actually the learning rate that was denoted in the lecture. So they are the same. And the max it is the maximum number of iterations that we let the gradient descent run for. So then what we do for all these iterations that we saw from the lecture, we first compute the gradient of f. And then we have a stopping criteria so that the derivative is not approximately 0. So it has to be greater than 0 in order for us to reapply the gradient descent procedure. And as we saw from the lectures, how gradient descent works, it just takes the previous iterate and it subtracts from it the gradient at that point times some learning rate. So the next value is just the current value minus step size times the gradient f at the current value. And then we simply append these values to some variable vals, all the next values. And then we use the gradient descent procedure to actually optimize this function that we have here. And these are the values of the optimums that this procedure finds. And what we can do, we can actually plot them. So again, this is what we saw in the lecture. We are starting from this point, then the optimum that the second optimum that it finds is here, then here until it reaches finally the optimum at 0. Actually, SciPy is also a library which can compute the minimum of functions for us. So if we have this function given as a lambda function, and then we want to plot it. So as we see, this is not a continuous function anymore, but it contains a sort of two disjoint parts. And then what we can do, we can optimize non-continuous functions using SciPy. And what we can do is that we can use this library SciPy to optimize a certain function in a certain range. So for example, this function over here, we can optimize it between some range. And for example, here we want to optimize in the range from 0.01 to plus infinity. So we want to optimize from here to here in this area. So we don't care so much about the left part. And as we can see with simply by looking at the plot, the optimum should be somewhere around here. But let's see what SciPy is giving for us. So let's just save this result in a variable res. This we use the minimize of f. We have to give to this function some initial guess 5. And we need to give a solver, so sort of one of the optimization methods that it uses. And we have to give bounds on which we want to find the minimum. So we have this bound minimum x and maximum x. And Mm. Did I forget a breakpoint? I think we also need to give some arguments. Okay, but here we're not setting the bounds correctly. And it should be okay now. Okay, so yeah, we have, we can actually plot this local minimum that we get from yes, so as I said, the minimum is more or less here because we're optimizing from 0.01 to infinity. And you could actually have it minimized on the left side. So for that, you would just change the borders where you want to optimize. And you would get something like this. All right, so let me check the time. I think I would stop here for the first part, and then we come in 15 minutes back for the second part. Okay, so see you then, everyone.
Anywhere you go, you belong. Anywhere you say, anywhere.
All right, so we are ready to continue with the second part of the workshop for today. So for those of you that are coming new, this is a continuation of the Calculus for Data Science workshop. So far we have seen the basic concepts for doing data science that are required from calculus, such as the definition of limit, derivatives, integrals. We saw gradient descent, and yeah, we are now continuing with the Hessian. So let's start by assuming that we have a function f, which is defined with taking values in Rn, from Rn to R. And then the Hessian matrix with respect to x, also denoted in this way, or simply by h, is an n by n matrix of partial derivatives. So in the first entry, we take a second derivative of f of x with respect to x1 squared. So we take it twice with respect to x1. The entry on the first row and the second column, we take the partial derivative of f with respect first to x2 and then to x1. And so on and so forth. We continue for all the entries of this n by n matrix. In general, we can write the more general formula for the Hessian matrix of a function f in Rn, where an ijth entry is simply given by this expression. One thing we have to note is that the Hessian is a symmetric matrix. So the Hessian of x ij is equal to so this would be the same. And one thing that we have to note is that the Hessian is defined only when f of x is real valued. So as we had from the beginning, f goes from Rn to R. So note that here we only have real valued values for f. So how could we relate the gradient with the Hessian? Well, the gradient is the analog of the first derivative for functions of vectors, and Hessian, on the other side, is the analog of the second derivative. So from before, we had that the gradient is related to the first derivative, which is also written in this way, and the Hessian is related to the second derivative. Some ambiguities that might arise is that for real valued functions of one variable, f from R to R, the second derivative is the derivative of the first derivative. So if we had function f of x, 3x 2x squared, and then the second derivative of x is this. right? For functions of a vector, the gradient of the function is a vector, and we cannot take the gradient of a vector. So this is not possible. One other thing that we have to keep in mind is that the Hessian is not the gradient of the gradient, unless we are having this simple case that we had here. This is almost true in the following sense. So if we look at the ith entry of the gradient, so if we look at the ith entry of x of I as the partial derivative of x with respect to xi, then we could take the gradient with respect to x of this expression. So if we do this, then we would get the second derivative of f of x. First, we take the derivative of x1, and then we take the derivative of xi. The second derivative f of x, the derivative of x2 first, and then the derivative of xi, and then again here I forgot 1, 2. So this is the second derivative of x. First we take the derivative of xn, and then we take the derivative of xi. So one thing that I forgot to mention is that when we have such an expression here, it means that first we differentiate with respect to xj, and then we differentiate with respect to xi. All right, so this is now the expression that we wrote here is simply the ith column or row of the Hessian. Thus, we can have this new expression for the Hessian. So we can write that the Hessian is actually written as the gradient of the gradient of f of x, 1, the gradient of the gradient of f of x, 2, gradient f of x, n. So then we would be sort of able to write that this Hessian of f of x is actually the gradient of the gradient of f of x transposed. So this is only true if we have such way of writing it. All right, so then what we're going to do is simply we're going to look at the gradient of we're going to find the Hessian for different kinds of functions. So as we know, we have linear functions, quadratic functions, etc. And the first that we do is that we compute the gradient of a linear function. So we have linear function f of x as a sum 1 to n of byxi. And then the gradient, we can take the gradient of f of x with respect to any variable xk. So this is just the partial derivative. And we could write this b1 x1 plus bn xn. And note that here we would have bk xk. As we saw before, we can consider all the other terms which do not depend on the variable xk as constant, so the derivative with respect to them would be 0. And that's why we can only consider the gradient of the term which has a bk in front of it. So the gradient is just the constant in front of it. All right, so we found this for one entry, that the derivative of f of x with respect to xk is this expression, bk. But actually, if we want to write this for all the entries, then we would write like this. And this would just be a vector consisting of all the entries from b1 to bk. And if we recall this from the single variable calculus, we actually had that the derivative of a of x is simply the constant in front of it. All right, so again, what we can conclude from this slide is that the gradient, when we have a multiple variable linear function, is simply a vector consisting the coefficients in front of the dependent variables x1 to xk. All right, then as I said, we can take the gradients of quadratic functions. So we have some functions of the form x transpose ax, which in the single variable calculus, it could be something like a constant times x squared, for example, that we had, plus 1. But now we have a symmetric matrix A. For those of you that couldn't attend the linear algebra course from yesterday, this notation just denotes n by n, or so-called squared matrices. All right, so we have this square matrix A, which we are multiplying from the left by x transposed and from the right by x. And we can use the definition of the matrix vector multiplication. And we can write this as the sum of i's from 1 to n, sum of j's from 1 to n, aij, xi, xj. And then we want to compute the gradient with respect to xk. So how do we do that? Well, we just plug here the expression for f of x. This is f of x. And then we sort of open up these sums, and we want to have them in such a way that we have a term which includes xk to the power of 2. And we want to have other terms which have them to the power of 1. And then this term actually is constant on xk. So the derivative of this term with respect to xk would be simply 0. The derivative of this expression would be just aij times xi for I, which is different from k, times xi. The derivative of this other one would be the sum for j different than k of akj. I think here I did a mistake, so it should be aik xi. The second one is the sum of j's different from k of akjxj. And here we take and this is now just a univariate function. And by univariate, I mean that there is only one dependent variable. So the derivative of it is by just taking the power and doing 2 minus 1. So it's 2 akk times xk. What we can then do, we can split this term into akk xk plus akk xk. And then we take one of the terms here and one of the terms here so that we can write these summations. And we actually see that this I and this j's are both running from 1 to n. So we can write this in a combined fashion as 2 sum I from 1 to n aki xi. All right, so then the kth entry of the derivative of f of x with respect to x is simply the inner product of the kth row. So this is the kth row of a and x. All right, and this is the kth entry. And if we want to write this for all the entries, then this would simply give us the two times the matrix A times X. All right, and yeah, again, so if we recall this from the single variable calculus, we have the partial derivative of ax squared is 2ax. All right, so yeah, we have to just remember now that in case of a linear function, we just have that the Hessian is equal to the vector of the coefficients. And in the case of the quadratic function, we have 2 times the vector of coefficients times the vector x. All right, so this was the derivative of f with respect to x. And then how we write this regarding the Hessian, we just do the second derivative of f with, first we take the derivative with respect to xl, and then we take the derivative with respect to xk. This is the derivative with respect to xk of the derivative of f of x with respect to xl. So for this, which is this one, use expression from the previous slide. And from the previous slide, we just saw that this is 2 sum a li xi. And then we take, once again, the derivative of this expression with respect to xk. So if we were to expand this, this would be al1 x1 plus a lk xk plus a n xn. So we just need this term because all the other terms would be constant with respect to xk. So this simply gives us 2aki or alk. All right, so this means that the Hessian or the second derivative is simply 2 times a. So again, from the single variable calculus, we had that the first derivative, let's say of x squared was 2x, and the second derivative was simply 2. All right, so one very important thing is that A is a symmetric matrix. So that's the condition that we have. All right, so we can have a recap what we saw so far. So the derivative of the sorry, B transpose X is simply the vector B. The derivative of the quadratic function X transposed AX is simply the 2 times the matrix A times X, and the Hessian is of the quadratic function is 2 times A, and in both cases we have to have that the A is a symmetric matrix. All right, so now we're going to talk about the so there was a question about the S. I think I already explained this. So this S is simply the set of symmetric matrices. So yeah, if you want to know more, you can check the linear algebra course, but like it's any n by n matrix basically. So it can be 2 by 2, 3 by 3, and in general n by n matrix. All right, so the next topic. Oh no, we had another question. The capital A and the small a are different things. Yes, so there are different things. A is a matrix and A in this case is just a scalar. So I'm just writing also the equivalent of the single variable calculus to make it easier to do the analogy between them. But they are different things. Right, so the next topic is the least squares. So we have an Rm by n matrix of full rank. And again, for those of you who did not attend the linear algebra course, this means that we say that a matrix is of full rank where the number of linearly independent rows and linearly independent columns is the same. So we don't have a matrix which has linearly dependent rows or columns which are more than m or n. And then B is in Rm such that it's not in the range of A. So this range of A, again from the linear algebra, is the space that is spanned from the space of columns or of the rows of the matrix A. So we are not able to find a vector x in Rn such that Ax equal to B. All right, so here what we want to do is we want to solve this Ax equal to B. A is an m by n matrix. B is n by 1, m by 1. No, this is x, sorry. This one is B. So x has to be n by 1. Again, from the linear algebra course, the second dimension of the first matrix has to agree with the first dimension of the second matrix, which in this case is simply a vector. So n and n, they are both the same. And when we multiply them together, it just gives us an m by 1 vector. All right, so the problem here is that we want to find a vector x such that Ax is as close as possible to B, measured by the Euclidean norm Ax minus B. So what we first do here, in other words, we have a function which we want to minimize. And the unknown in this case, we are given the matrix A and we are given the vector B. So the unknown here is x. So our function is f of x, Ax minus B. And here we want to minimize this difference. So what we do, we start by opening up this Euclidean norm, and we can express this as a dot product between Ax minus B transport and Ax minus B. And if we simply open up this square, we would get x transposed A transposed Ax minus 2B transposed Ax plus B transposed B. What we saw so far from the calculus is that the gradient, which in this case is with respect to the vector x, just gives us the minimum of an objective function. So we take the gradient with respect to x of this expression, and we see that the terms that depend on x is this one. Only these two terms, the last term actually does not depend on x. So the gradient of this expression is then, this gives us 0. And here, we just use what we got from the previous slides. So what we said here, we use this readily, and we get that the gradient is 2A transposed Ax minus 2A transposed B, and we just set this to 0, and we solve this for x. So the gradient of f of x equals to 0, 2A transposed Ax minus 2A transposed B equal to 0. A transpose AX equals A transpose B. We multiply from the left with A transpose A. So this just gives us A transpose A inverse A transpose B. All right. So yeah, there we have the formula for the least squares. So the solution to AX equal B. All right. One another thing we can do is that we can look at eigenvalues as an optimization problem. So yesterday we saw how we computed these eigenvalues, and we saw a lot of examples. The way that we did was to just compute this characteristic polynomial, find its eigenvalues, then find the corresponding eigenvectors, and then we had our so-called eigen decomposition. And so again here, now our optimization problem is this one. So A is a matrix that we know, and we want to, in this case, maximize X transpose AX, such that, as we saw, these eigenvectors have to be unitary vectors. So their Euclidean norm is equal to 1. Usually in optimization, it's very well known, the so-called Lagrangian methods, where we take this lambda Lagrange multiplier, which is associated with the equality constraint. So the Lagrangian problem then becomes f of x minus the Lagrangian multiplier times the length of the vector. And in this case, this is simply our function is x transpose AX minus lambda X transpose X. As we saw from before, the gradient gives us the optimal point. So what we do, we just take the gradient of the Lagrangian and we set it to 0 to find the optimum X star. And the gradient of this function is just this. And from what we saw from the previous slide, the gradient of this expression is just 2A transpose X. And the gradient of this expression is minus 2 lambda X. And then we want this to be 0. So 2A transpose X minus 2 lambda X equals to 0. A transpose X equals to lambda X. So we have a system of linear equations. So by definition, these were eigenvectors of A, and the only points that can possibly maximize or minimize the objective function that we had from before, assuming norm 1 are the eigenvectors of A. Right, so far I don't see any question in the chat. All right, so far we saw the basic concepts from calculus. I think these are more or less the concept that one needs to do data science from calculus. And now we're gonna go more towards deep learning and explain how we can sort of use all these gradient techniques that we learned from single and multiple variable calculus to optimize a neural network. So just to give you some more background on neural networks, I think neural networks have been out actually for quite a while, and they're being deployed very successfully in real-world applications. They're achieving state-of-the-art performance in computer vision, natural language processing, robotics, games, engineering, in medicine. And one very important problem with regard to neural networks is how to optimize them. And this is where calculus comes into play. So the problem is that with neural networks is that they are huge. We are not dealing anymore with functions of few variables, but deep neural networks are becoming larger and larger, and they contain sometimes 1 million of parameters which we sort of want to optimize. And of course, we are not optimizing neural networks by hand. That would be a disaster if we would start. But we are doing that. We are using so-called optimization technique called backpropagation, for which there also exist a lot of online solvers in Python, such as automatic differentiation, which gives us the optimized parameters. But nonetheless, we need to know how all these inner workings of neural networks work in order for us to know how to optimize and what sort of neural network to choose, etc. All right, so the very first concept in deep learning is the concept of the perceptron. So the structure of the perceptron is actually really simple. We have this inputs x1 to xn, and then what we do in the perceptron, we learn these coefficients w1 to wn. And what we mean in deep learning with learning is that we just find a way how to calculate this w1 to wn's. So we just find a way to optimize them so that they are optimal for our use case that we are using. I mean, the perceptron is the very first and the simplest algorithm, so nobody's using it anymore, but it's the basic building block for all the neural networks that we are using nowadays. So I think it's very important to give a brief explanation of it. And as soon as we apply these weights w1 to wn and we sum them up with our inputs, as denoted here, so we take w1, we multiply it by the first input, plus w2, second input, plus wn xn. We also here have a so-called bias or a threshold. So this is, as far as I recall, it is also mimicking the way that the human brain works. So in order for our brain to process a signal, it has to be like this summation has to be stronger than some threshold in order for this to fire up. So in order for it to cause some something in our brain. So this is just mimicking the human brain. And then we can express this, as we saw yesterday in the linear algebra course, we can express this as the inner product of two vectors w and x, where on each entry we apply a so-called threshold or a bias b. On top of it, we have a so-called activation function, which in this case is just the sign of z. So the sign of Z is simply defined as 1 for all the z's greater or equal than 0, and -1 for these z's. And if we were to plot this, it would look something like this. So this is the sign function. All right. And the learning task in deep learning is that we are given this input data x1 to xn, which is some data in Rn. So they are all vectors in Rn. As I said yesterday, we are using vectors to denote our data that we want to experiment with. And in deep learning, we are also given this set of training data. So for some instances of data, we also know the true correct label. And according to this training data, then we are able to do prediction for the future data, which we still haven't observed. So the goal is for us to learn a collection of parameters W and B such that we... Sorry, I went too far. So the goal is for us to learn a collection of parameters W and B such that we minimize the loss between the true label and the label that we predict. So what is this perceptron doing? As I said, we are taking the inputs, we are applying to them this coefficients which we later learn. And finally, this is predicting for us a label. So this is a label. So if you recall from yesterday, we had this image, let's say, of a human in this case, or I don't know. I mean, usually in deep learning, we are experimenting with cats. And then you take this cat through the neural network, and this gives you the label cat. So for some points of data, for the training data, we already know these labels, and then we also predict using the coefficient W. So we train this neural network to learn to classify new instances based on what we have seen so far. So we want that our neural network is working very well on this training data. And in order to do so, we impose a loss function. So we want that our prediction and the actual label to be as minimal as possible. And usually for the loss, we use in machine learning the so-called cross entropy, or so at the end of the day, you just use some distance between your predicted label and the original label, because at the end of the day, both of these are just some vectors, and you can sort of compare them using the metrics that we have seen so far. And then the predictions of the perceptron for each data point, we sort of just take the new data point, we apply the coefficients W, we sum with the threshold, we apply an activation function. And then our question is, can we find, so does there exist a set of parameters W and B such that the prediction of our perceptron, so this is the prediction, equals the true label. So in this really simple example, we have the simple task of splitting or sort of classifying the circles and the squares. And we want to find a line between of them, which separates circles from the squares. So our question now is, can we find such a line so that all the circles lie on one side and all the squares lie on the other side? And as we see in this case, there exist actually infinitely many solutions. And this is actually very easily computed using the perceptron algorithm. So what we do in the perceptron algorithm, we simply initialize W by 0 and the bias or the threshold by 0. One thing to note here is that I am denoting vectors in bold and scalars is just normal notation. And then how the perceptron algorithm works is that it repeats for j from 1 to m. If one data point xj is correctly classified, it just continues to the next point. So you are done with this point. And if xj is wrongly classified, so if the predicted label is different from the actual label, we update this weight. So we modify our classifier to also correctly classify this data set, which was data point which was wrongly classified. And the way that we do is that we just do these two steps. So we do w plus some learning rate eta times xj, tj, and for b, we have b plus eta times tj. So for those of you that were very attentive, this should already recall you something. So if you recall from around an hour before, this learning rate we had in gradient descent. So yeah, we are updating these weights using gradient descent, and we repeat this procedure until all examples are correctly classified. All right, so then we have this proposition which says that actually the perceptron is equivalent to the gradient descent of the so-called hinge loss. So the hinge loss, again, before we were writing functions of dependent variables by f of x, and now our goal is to find w and b. So now our dependent variables are w and b, and our loss function is not anymore f, but is lj wb. And this proposition says that the perceptron is equivalent to the gradient descent of the so-called hinge loss, which is simply given by 1 over m, sum j from 1 to m, the maximum between 0 and minus zj tj. All right, and in order to prove this, we can do this separately. So the claim is that perceptron is equivalent to hinge loss, gradient descent of hinge loss. And the hinge loss is just given by this expression. The max 0 minus zj tj . All right. So this claim is saying this, and in order for us to prove it, we start by doing gradient descent on the hinge loss. If you remember, gradient descent was just xt, so x on the time step t, minus some learning rate times the gradient of x at xt. So this is the gradient descent update rule. So what we need to do is we just need to do this gradient descent update rule on the Hinge loss. But now we don't have just one dependent variable x, but we have w and we have b. So then we do w minus the learning rate times the gradient of Lj. So we take each of them separately with respect to w. And as we see, Lj is just max of 0 minus Zj Tj. So then we just have w minus eta times, we have 1, so we have to know the So where is this one coming from? Well, this one is coming from the fact that we're taking here the maximum between 0 and this. So whenever this is greater than 0, then we have the value for this. And whenever it is smaller than 0, then the maximum is 0. So then this expression would be 0. And then the gradient of this with respect to w. All right. So then we just have w minus eta 1. Another way to write this minus zj tj greater than 0, it just means that they are not equal to each other. So this would be the case when the predicted label and the actual label are different from each other. And then we have minus gradient of zj with respect to w tj. And this is simply w plus times so the gradient of zj with respect to w is simply xj tj. Why? Well, zj, as we saw before, is when we apply this weights w to xj plus b. So this is just the definition of the perceptron. So yeah, when we take down the gradient with respect to w, this is a constant. So we are just left with xj tj. All right, and this then concludes the proof. And the proof for the parameter b could be done in a similar fashion. So I will not go through it here, but it's literally the same steps. You just substitute w with the b. All right, so as I said, the perceptron is the basic building block of deep neural networks. So what we then do, we just stack together multiple perceptrons into a deep neural network. So if you recall from the previous slide, this alone would have been a perceptron. But now we have one perceptron, 2, 3, 4, 5, 6, and so on and so forth. So deep neural networks are just an extension of the perceptron to multiple so-called hidden layers, where in layer 0 we have the inputs. And these are so-called hidden layers. And this is the output layer. Yeah, so we just stack multiple perceptrons together and we generalize the formulation where Z now is the output of a multi-layer neural network with parameters theta. And as we saw so far, we saw a way to optimize the loss, the hinge loss, so that we find the best parameters for the perceptron. So now how do we optimize neural networks? This is the question that we are dealing with. All right, so the question that we have is actually how hard is to compute the gradient of the error with respect to the model parameters. So yeah, this is just what we saw before. Can we do gradient descent? But now the problem here is that this parameter, this part here is actually containing a lot of parameters. We just don't have a W and beta, which we had in the case of perceptron, but we have multiple variables, which we are denoting here by a W. So we are having all these biases, AK, which before were denoted by B, and we have these WJKs. So we don't simply have W and B, but we have way many more parameters. All right, so the idea is here. How do we compute the gradient of the loss with respect to parameters? We could simply use the definition of a derivative, which we saw today. So by the definition of the derivative, we have some loss function, and we have simply the limit when epsilon tends to 0 of the loss of theta plus epsilon times some indicator vector for the parameter t, minus the loss of theta over epsilon. And what is good about this definition is that it is applicable to any error function L. So L could be hinge loss, cross entropy, etc. However, one problem with this approach is that we need to reevaluate the function as many times as there are parameters. So this is slow for a large number of parameters. So yeah, here, we need to do this for all the parameters that we have here. So for this one, for this one, this one, this one, for all these arrays that we have between them. And the problem is that neural networks, as I said, nowadays, they are becoming larger and larger, and they typically have between 10 to the 3 to 10 to the 9 parameters. So this means that numerical differentiation becomes unfeasible, actually. So for that, we need to use high precision Another thing that we need to use, especially when we implement this, we need to use high precision. We need to define variables, for example, in Python with high precision, so like float 128 or something like that, because epsilon and the numerator are very small. So like we would need them to store a lot of numbers, and this just means that we are making this slower and slower. The problems that are with this approach are also the fact that this function, like the loss of a neural network, is most of the cases non-convex and non-linear. So as we saw before, non-convex it looked something like this. So we cannot really apply gradient descent. And it also is non-linear, so it's not, it could be something like we saw again before, a function something like this. So it's really hard for us to find the minima of such a function. The computation of this gradient is tricky to be done by hand. So can we do this automatically? A general rule to find the weights theta was actually not discovered until 1974 by Paul Rebosch, in 1985 by LeCun, and 86 by Rumelhard et al. So actually all these rules were first for the perceptron, and backpropagation algorithm that I will show you in a bit is actually even more recent. So the idea is that we need to compute the gradient of the loss L with respect to Wjk, so that we compute the error of the output and we propagate that back to the neurons in the earlier layers. And this is then making possible for us to compute the gradient. All right, so here we would also need to recall the chain rule that we had from before. So if we have some parameter or variable of interest theta q, and the output of the network z is linked through a sequence of functions. So a is a variable which depends on theta q, b depends on a, and z depends on b. So this is the independent one. And then applying the chain rule for the derivatives, the derivative with respect to the parameter of interest is a product of local derivatives along the path connecting theta q to z. So as we saw before, I hope you recall where delta z was so this was when we had only 2. But now we have 3 dependent variables. So the gradient of z with respect to theta q is just, well, we first do the gradient of z with respect to b, the gradient of b with respect to a, and the gradient of a with respect to theta q. All right, so this is the chain rule. And the multivariate chain rule is that the parameters of interest might be linked to the output of the network via multiple paths, which are formed by all neurons in layers between theta q and z. So we don't have only this theta q, a, b, z, but actually we might have many more paths as we saw in neural networks. So we have this output layer, and we had many more dependent variables in the middle, and then theta q is the variable with which we want to find the gradient. So in the multivariate scenario, the chain rule, it simply enumerates all the paths between theta q and z. So when we now want to find the gradient of z with theta q, we simply do the summations of all these paths. So first this one, then this one, then this one, and so on and so forth. So this is just defined sum over I, sum over j, gradient of AI with respect to theta q, gradient of bj with respect to aj, gradient over z with respect to bj. And these sums over I, sums over j run over all indices of the nodes in the corresponding layers. So this is a nested, so-called nested sum. So the complexity grows exponentially with the number of layers. So as many layers as we had, we first have to sum over j. Then for each I independently, we have j sums. So we have exponential with respect to number of layers. All right, so what we could do, we could rewrite the computation and we could perform the summing operation incrementally. So yeah, could we maybe do the summation first for this part and then for this part and then for this part? So without doing this that we had from before. And maybe we could already use this summation for this part here and this for this part here. So we could reuse intermediate computation for different paths and parameters for which we would like to compute the gradient. So we just open up this summations, which we had from before. And first we sum over all j's, the grades of bj over aj's, and the gradients of z with respect to bj's. And we simply denote this by some delta I. The resulting gradient computation with respect to all parameters in the network is thus linear with the size of the network. So we are reusing this for all the i's, so we don't have to do for every I again summing up j elements. So now we don't have exponential anymore, but this is a linear procedure now. All right, so this was a lot of theory, I think, so far. So let's just look it up via an example. So assume we have this really simple neural network where we have two hidden layers. We have the input layer and the output layer. And we have this following architecture. So first, what we need to do is that we need to compute the forward pass. So the forward pass is like we start from the inputs and we go to the output. So we first denote this A1 by X1 and A2 by X2. And then here we compute the first intermediate step. We just multiply A1 by W13. And then in A3, we apply an activation function, because in each of these nodes, we actually have activation functions, which in this case, we are working with 10H. And then in Z4, we actually have two arrays coming towards A4. So we do A1 multiplied by W1K plus A2 W2K. We again apply the activation function. Then we go to the next hidden layer. Z5 is A3 W35 plus A4 W45. Again, we apply the activation function. We compute again the Z6, which is an intermediate layer before we compute the A6. And finally, for we compute Z out, which is this part here now. So A5 V5 plus A6 V6. And we apply again here, I think, the Hinge laws. So the output of the neural networks times the true label. And we want to find the maximum of this product and 0. All right, so far so good for the forward path. What about the backward path? So now that we know the forward path, this is just the forward path from the previous slide. We next want to compute the gradients of this loss with respect to all the parameters. So, as I said, we actually learn all these parameters. We, in a sense, fine-tune all of them. We don't know the actual value of them. So in order to do that, we start by calculating the gradient of the loss with respect to very last node of the last layer. And as we saw this from before, where we computed where we saw that the perceptron is just the gradient descent of the hinge loss. The gradient of the hinge loss is just this one. So as soon as we have the gradient with respect to this variable, we can then compute the gradient of the loss with respect to this variable and with respect to this variable, and we save these instances in some variables delta out. So now for the gradient of the loss with respect to V6, we just use the chain rule. So this is the gradient of Z out with respect to V6 times the gradient of the loss with respect to Z out. But the gradient of Z out with respect to V6 is simply A6. Well, this is true because A5 V5 plus A6 V6. So the gradient of Z out with respect to V6, this is constant. The gradient with respect to this part is just A6. And we save this in some instance delta out. In a similar fashion, we calculate the gradient of the loss with respect to V5, and we have this. All right, so as soon as we have found these quantities, so delta out, we can compute now the gradient of the loss with respect to this and with respect to this. Again, we use the chain rules, and these gradients are just V6 times delta out. So we reuse, this stuff is very important, so we reuse this variable delta out from the previous slide, and we have V6 and V5. All right, so then as soon as we have found this delta 6 and delta 5, which are the gradients of the loss with respect to A5 and A6, we compute the gradients of the loss with these variables, with respect to these variables. Again, we reapply the chain rule. So the gradient of the loss with respect to W46 is the gradient of Z6 with respect to W46, gradient of A6 with respect to Z6, gradient of loss with respect to A6. So we just have this path. So apply chain rule on this. In a similar way, we find the gradient of loss with W45 and W35. All right, and then we are able to compute this delta 6, delta 5, delta 4, and delta 3. So these we already had from the previous slides. And again, for delta 4 and delta 3, we use the chain rule, but note here that now we have the summation. Well, we need the summation because we have two paths now. So we don't have just one path when we take the gradient of the loss with respect to A4, but we have two paths, so we do summation. First the chain rule of the first path, and then the chain rule of the second path. And here we have that A6 is tanh of Z6. So gradient of A6 with respect to Z6 is tanh of Z6. All right, so one important thing to note is that here we are reusing. Again, this is what makes this procedure linear and not exponential anymore. So we are not recalculating this for all the previous layers, but we are reusing them. All right, so we have delta 4 and delta 3. Again, we finally want to calculate the gradients with respect to the last A1 and A2 parameters. But before we do that, we need to calculate the gradient with respect to these, which we then readily use. Again, we apply the chain rule. So the gradient of the loss with respect to WD4 would just be this root with respect to W14 and W13. And we reuse the values for delta 4 and delta 3. All right, so what we are seeing so far is that we are propagating the gradient of the error from layer to layer, and we are using the chain rule. So we are reusing this W case from the previous layers, and the gradients of the new ones are just Wjk, the gradient of G with respect to Zk. So we can actually write these two formulas, which is just basically a way to write these two and a way to write these two. So as we see, for all of these, we have A times the gradient of tan H times deltas, and here as well. Here we have W's, here we have A's. So this is important to know. W's, A's, deltas, deltas. So also here, when we write in a general way, here we are left with W, the gradient of G, and here we are left with A's gradient of G, and delta K, delta K. And furthermore, we can write this more as a matrix vector product. So if you want to really know how this works out, you can again have a look at the matrix vector multiplications that we had from the course of linear algebra. So this delta of the layer L-1 is just defined as the vector of W's from layer L-1 to layer L, the gradient of G dot product with delta L's, and the gradient with respect to the weights from layer L-1 to L is simply the vector A, gradient of G dot product with the deltas. All right, one thing to note is that the gradients of, what does the O mean? Also, this is the dot product when you have, like, I think yesterday we just used the outer. From the definition yesterday would be the outer dot product. It should be in the middle of the slides from yesterday. In general, the gradient of the loss with respect to when going from layer L-1 to L is usually very bigger, way bigger than the gradient of the loss with respect to weights from L-2 to L-1. So the more left you get into the network, the more the gradient vanishes or gets smaller. Well, this is true because tan H has gradients in the range from 0 to 1. So if you keep multiplying one number with some value between 0 and 1, then this value is approaching 0 exponentially with n. And there are ways to circumvent this problem. This is the so-called vanishing gradient. So after some point, you might actually be having 0 gradient, so then you can learn anything anymore. And how we could circumvent this is by using many labeled data. So this is well possible for images, and just consider the amount of images that we generate every day. Another way to circumvent this is by training longer, which is also possible nowadays with using GPUs. Or using better weight initialization, for example, using this technique, Xavier or Blorod. Another way is to regularize with the so-called dropout, so where you just set some hidden nodes of the hidden layers with 0, or use some other activation function such as rel. So far we use the 10H activation function or the sign function, but actually we could choose some other nonlinear activation functions such that its gradient is defined almost everywhere, and a significant portion of the input domain has a 0 gradient. We can choose it in a way that the gradient is informative, so it indicates increase or decrease of the activation function. Some commonly used activation function are the sigmoid, which is given by this. This is very used in machine learning, the tanh, which we saw before, and the relu, which we saw before. And some problematic ones are given by these ones. So yeah, they sometimes lead to vanishing gradients. All right. And then we will finally see automatic differentiation. We will see that this is actually a procedure which is implemented in PyTorch, and it automatically generates backpropagation from the forward equations. So what you really need to do in Python is you just need to do this very first forward pass. So you just read through your architecture, and you don't really need to do this backward passes that we did before. This technique is widely available in deep learning libraries such as PyTorch, TensorFlow, JAX, so like libraries that we saw before. So yeah, we don't need to do backpropagation, we just need to program the forward pass, so backward pass comes for free. This also motivated the development of neural networks that are way more complex and with much more heterogeneous structures, such as ResNets, YOLOs, transformers. So far, like this architecture that we saw, it's also called feed-forward neural networks because we have this more regulated structure, but neural networks can be way more complex. In few cases, however, it's still useful to express the gradient analytically when we, for example, want to analyze theoretically the stability of a gradient descent procedure. So now that we saw how we do backpropagation, we are able to actually give a procedure how we could train neural networks, so how we could train these models which are achieving state-of-the-art performance in many areas. So we can train neural network to classify, for example, images. So we simply initialize theta at random. So theta, as I said before, includes all these variables, W, J, K, and biases A's. And then we repeat for T steps. We first compute the forward pass. We use backpropagation to extract the gradients of the loss with respect to theta, so with respect to all variables that we have in our neural network. And then we perform a gradient step. So this is the gradient step that we had before, where we have chosen some learning rate gamma. Of course, this is like the most basic training neural network algorithm. It's not going to get you any best accuracy whatsoever, state-of-the-art accuracy, but it's the first algorithm that you can try out to train your very first neural network. All right, so in summary, we saw that a gradient descent can be used to minimize the error of classifier, for example, Perceptron, neural network, and backpropagation. We saw that error backpropagation provides a computationally efficient way of computing the gradient compared to the formula for numerical differentiation. So we saw that by definition, this is not the best thing to do. Error backpropagation is direct application of the multivariate chain rule, where different terms can be factored due to the structure of the neural network graph. We saw different techniques to circumvent vanishing gradients, and I will also now show that we actually can do this using automatic differentiation in PyTorch very easily. So yeah, we have some minutes left. Again, you can find all the slides on my personal website, and yeah, if you have any questions, you can either use Twitter or my email. So now let's go to the coding. right? All right, I think we were left on the very last exercise. Yes. So we want to do backpropagation, and we want to focus on programming the forward and the backward computation while implementing the neural network. So the neural network that we are considering is the one depicted below. So we have the input layer X. Maybe I can increase it a little bit. We have the input layer X. We have the matrix W1 of variables B1, the biases. Then we have the second hidden layer, the third hidden layer, and then we have the output. So first, we define this function get data. So we have a NumPy array given by this vector. And we have the t, which is the predicted label. And then we also have these parameters W1, W2, W3, and W4, and B1, B2, B3, and B4 for the neural network. So we just run this. So as I said, we will just use PyTorch for this task. We want to use existing neural network objects in PyTorch library. Most of the code is already implemented, so you're only asked to compute the forward pass and the error gradient. All right, so we first get the data and the parameters using the get data and get params functions that we defined above. We convert to first PyTorch objects, so we convert all these matrices into PyTorch objects. And then we build the neural network. So in PyTorch, this is actually really straightforward. You just sequentially add linear layers, and then you add the random activation function. So in this case, we have 3 hidden layers, and then we have activation functions, and we finally have at the end here just a linear, here would be just a linear map at the end. And we don't apply an activation function at the output layer. And then we set the weight and biases by W and B. So then we want to compute the forward pass and the error for the gradient. This is really simple, and so you just do net.forward. So you take your data through this neural network. After you have taken your data through your neural network, you compute the loss between your prediction and the actual true prediction, which was given by T. Here we are using the mean squared error loss, where we just compute the difference between the prediction and the true label squared. Not the true label, sorry. Here we have continuous data, so we don't have labels. That's why we're using the mean square error. So we compute the loss between true and predicted values squared, and we take the mean. And then we simply do the backward step using this error.backward. And then we show the error of the gradient with respect to the first weight parameter. So we show the, like if you recall from the lecture, this architecture that we had, we are showing the gradient of the very last layer with respect to the very first ray parameter. So this is now running. NumPy is not defined. Okay, so yes, we get a gradient of the first weight vector of 1 minus 5.4, 1.54, 22822. So yeah, then we can simply repeat this procedure for more values. Right. I think that's all for today. We're also at the end. All right, so you have all the materials and the link to the notebook. I would like to thank all of you for joining also for today's session. I hope you had a great time. And yeah, if Hui doesn't have anything to add, I will just close this session here.
Thank you very much, Mr. Person.
Thank you.